So one phrase that's quite commonly heard is minimum viable population size. This is a concept that was advanced back in the early days of conservation biology, and I've got the definition of it up here on the screen. Essentially, the idea was we should figure out what's the smallest isolated population with a 99% chance of remaining extant, that is, not going extinct, for 1,000 years, despite the foreseeable effects of demographic, environmental, and genetic stochasticity and natural catastrophes. Sorry, that's 3 flavors of stochasticity plus natural catastrophes. The problem with this definition is that the authors didn't provide any way to actually calculate it. One popular set of definitions popped up around genetics, and in particular a notion of effective population size, which we'll come to in a moment. The basic idea was that an effective population size larger than 50 would avoid immediate inbreeding effects, and an effective population size bigger than 500 would prevent serious loss of genetic variation over time. And the reason why conservation biologists were concerned about genetic variation in small populations has to do with genetic drift. So you may be familiar with the concept of genetic drift, that is, random changes in the frequency of different alleles for a given gene. When populations are very small, those random variations up and down can easily lead to a loss of variation, which means that the frequency of one allele goes to 100%, and the other allele or alleles are lost to the population. Geneticists describe genetic variation using a number called heterozygosity, and heterozygosity is simply the number of, or sort of the sum, what's the best way to describe this? It's the average value of having 2 different alleles at a given locus divided by the number of loci, that is, genes, that you're looking at. So if you've got 10 different loci and 7 of them have different alleles, then you would have a heterozygosity of 0.7. If you know the frequency of each of your alleles, and there could be m alleles at any given locus, then the effective heterozygosity is going to be calculated this way. So 1 minus the sum of the frequencies squared. You don't need to keep that in mind. But the basic idea is that your heterozygosity is going to be highest when F is around 0.5 if you've got 2 alleles, 0.3 for example if there's 3 alleles, and so on. So what about effective population size? So now we know we're measuring heterozygosity. What about effective population size? Well, the basic problem with genetic drift is that it happens faster when you have different numbers of males and females, because that means the opportunities for mating with a random number of individuals are constrained. So we calculate the effective population size using this expression: 4 divided by the sum of the reciprocal of the number of females plus the reciprocal of the number of males. So if the number of females and the number of males are equal, then the effective population size is going to be equal to the sum of the males and females. But if they differ, if there's a departure from the equal sex ratio, then the effective population size is going to decline compared with the actual population size. The idea behind the effective population size is that it's how big an ideal population would be that loses heterozygosity at the same rate as the real population. And so when the sex ratio is completely balanced and there's random mating, then your effective population size, this ideal population, is exactly the same size as the real one. But if the real population has a skewed sex ratio, then the effective population size will be reduced. So over here in the left-hand panel on the x-axis is the proportion of males in the population. So a perfectly balanced sex ratio has half of the population as males. And on the y-axis is the effective population size divided by the total population size. So when we have a balanced sex ratio, that ratio of effective population size to total is 1. And that's where we're at right here. As we deviate away from that perfect sex ratio, either having too few males or too many males, then the effective population size declines away from the true population size, the real population size. And in the extreme, of course, if you have 0 males and only females, then your effective population size is 0 because there's no mating involved at all. So you're going to drop out very fast, same as if all you have are males. Now, heterozygosity, or the annual change in heterozygosity, also decreases with population size. Rather, the rate of loss increases. So when our populations are very large, around 500, the rate of loss of heterozygosity is very tiny. This curve is very close to 1. As the population shrinks, this curve starts to accelerate faster and faster and faster, and then it starts to drop off quite rapidly. So where the 50 comes from is that if you look right here, 50 gives you a value approximately right there, okay, of about 0.99, or just a bit bigger than 0.99. So this is the 50 individuals, a nice round number, and it's at the point where before the heterozygosity loss starts to accelerate very rapidly. And 500, by contrast, is very close to 1, so that means no loss of heterozygosity for populations of that size. The dashed line in this case is what happens if you shrink, if your sex ratio is 0.3, so that is 30% males, 70% females. So you're down here somewhere. And what you can see is that it actually doesn't make that big a difference compared to the effect of small population size. So even quite large departures in sex ratio aren't really causing very much of a decline in heterozygosity over what you would get at the same population size with an ideal sex ratio. But in any case, even when you're down here around 10 individuals, the rate of loss of heterozygosity is about 5% per year. You've got much bigger issues when you've only got 10 individuals per 10 individuals in your population than the loss of heterozygosity. Here's what that equation looks like for heterozygosity. So the heterozygosity next year divided by the heterozygosity this year, that's the change in heterozygosity, just 1 minus 1 over 2 times the effective population size. So that rule of thumb that people often use, any 50 implies a change in heterozygosity of 0.99. That is, you lose 1% of your heterozygosity per generation. 500 implies delta H is 0.999, so you're losing 0.1% per generation in heterozygosity. So that's a very slow loss rate. So that's where the rules for 50 and 500 come from in terms of the effective population size.